What factors contributed to the extinction of Ammonites, whereas Nautiluses persisted? During the Cretaceous-Paleogene extinction event, it is likely that no one is unfamiliar with Ammonites. It is renowned as a quintessential organism of the Mesozoic era, alongside dinosaurs, and as a species that vanished from Earth following the Cretaceous extinction concomitantly with the dinosaurs. Nonetheless, some individuals occasionally observe this nautilus in documentaries and mistakenly believe that Ammonites survived the Cretaceous mass extinction and evolved into their progeny. Indeed, these two represent distinct categories, yet they are entirely independent entities. The two varieties are categorized into the subclasses Ammonoidea, Nautiloidea, and Coleoidea, with the squid classified under the order Decapodiformes within the subclass Coleoidea and the octopus under the order Octopodiformes. The aforementioned nautilus is classified here, whereas the ammonite is categorized in the subfamily Ammonoidea. At present, all members of the subclass Nautiloidea are extinct, whereas in the subclass Cephalopoda, only the order Nautilida and the family Nautilidae persist, with merely 6 species of nautilus extant today. The figure illustrates that ammonites are more closely related to octopuses and squids than to nautiluses. However, despite your assertion upon examination, the two are quite analogous. In what locations on Earth do these two differ, and in what manner? The nautilus possesses a mostly concave morphology with the septum partitioning the inside of the shell, oriented towards the opening where the organism resides. Conversely, ammonites exhibit a convex or uneven morphology. The most significant distinction is the location of the siphuncle. The clam's siphon is situated centrally within the mantle. The slender siphuncle, filled with bodily fluid, collects water entering the shell chamber by osmosis and releases gas back into the chamber to regulate buoyancy. Conversely, ammonites possess siphuncle tubes that are linked to the exterior of the shell rather than the interior. One of the most remarkable and often overlooked discoveries in the evolutionary history of marine life is that the nautilus predates the ammonite by a significant margin by nearly 80 million years. While ammonites are often celebrated as iconic fossils of the Mesozoic era, the nautilus quietly holds the title of one of Earth's most ancient surviving life forms. This unassuming cephalopod first appeared in the late Cambrian period of the Paleozoic era, approximately 490 million years ago, making it older than even the coelacanth, a fish often hailed as a living fossil. In contrast, ammonites emerged later during the early Devonian period around 410 million years ago. Though they are both members of the subclass Cephalopoda, their evolutionary paths, ecological niches, and eventual fates diverged dramatically over time. The early ancestors of both the nautilus and ammonite bore straight, elongated shells, a primitive design thought to be more hydrodynamically efficient in a relatively predator-free ocean. However, as marine ecosystems grew more complex and apex predators such as early sharks, placoderms, and marine reptiles emerged, both groups experienced strong evolutionary pressure to adapt. One major adaptive leap was the transition to tightly coiled shells, a form that provided enhanced protection, better buoyancy control, and a smaller surface area for predators to attack. Both lineages survived multiple global extinction events, including the Great Ordovician biodiversification event and the devastating Permian-Triassic extinction, the most severe mass extinction in Earth's history, which eradicated an estimated 90% of marine species. Yet both nautiluses and ammonites endured, highlighting their resilience in a turbulent biosphere. Despite this shared resilience, their evolutionary success in later eras was markedly different. Ammonites experienced an extraordinary boom during the Mesozoic era, especially in the Jurassic and Cretaceous periods, diversifying into thousands of species that occupied a broad range of ecological roles in marine food webs. In fact, their success during the Mesozoic was so extensive that they became emblematic of the era's marine life, hence the nickname index fossils of the Mesozoic. One of the reasons ammonites are so valuable to paleontologists lies in their shells, which are internally divided by septa walls that separated gas-filled chambers used for buoyancy. Where these septa met the outer shell, they formed distinctive patterns called suture lines. These patterns evolved over millions of years, becoming increasingly elaborate. Paleozoic ammonites, such as goniatites, exhibited relatively simple wavy suture lines. But by the Triassic period, ammonites had developed more complex lobes and saddles in their sutures, culminating in the highly ornate fractal-like patterns of Cretaceous ammonites. Each suture configuration reflects not only taxonomic lineage, but also the geological time period, allowing scientists to date sedimentary rock layers with great precision. These intricacies made ammonites invaluable as biostratigraphic markers. In fact, entire rock sequences across continents have been correlated based on ammonite fossils alone, a testament to their widespread presence and rapid evolutionary turnover. Their global distribution, short lifespans, and quick morphological changes meant they left behind a detailed chronological record of Earth's history. Yet despite their success and importance, ammonites could not withstand the catastrophic events of the Cretaceous-Paleogene extinction 66 million years ago. Following the asteroid impact that struck the Yucatan Peninsula, a chain of ecological disasters including darkness, cooling, acid rain, and food chain collapse erased them entirely from the planet. Not a single species survived the event. In contrast, the nautilus, less diverse, slower to evolve, and dwelling in deeper, more stable marine environments, survived the cataclysm. Its conservative lifestyle, slow metabolism, and reproductive strategies centered around large yolk-rich eggs gave it a surprising edge during times of environmental crisis. The story of these two ancient lineages serves as a powerful evolutionary parable. Ammonites, dazzled with diversity and innovation, rising to dominate the oceans for hundreds of millions of years. Nautiluses, with their understated persistence, managed to survive where their more flamboyant cousins fell. In the end, it's a quiet testament to the fact that longevity in evolution often belongs not to the flashiest or fastest, but to the most adaptable and enduring. Conversely, the parrots endured. Despite belonging to distinct lineages, if their appearances were analogous, their ecological niches would likely have been comparable as well. What factors contributed to the extinction of this species, and what enabled this species to endure? Ammonites saw significant speciation during the Mesozoic era, exhibiting a variety of unusual morphologies and reaching diameters of up to 1.8 meters, while diversifying into over 5 genera. Conversely, at that time, only 4 species of parrots existed within a single genus, and their lives were not very different from those of today. Dr. Neil Landman, a leading paleontologist at the American Museum of Natural History, has long studied the evolutionary rise and fall of ammonites. He attributes their staggering diversity, spanning thousands of species with an immense range of shapes and sizes, to one central biological factor: their exceptionally high metabolic rates. In a groundbreaking study published this year, researchers employed advanced carbon isotope analysis to estimate the metabolic rates of ammonites and compared them with those of modern nautiluses and related marine organisms. The findings were remarkable. Ammonites exhibited metabolic rates that were approximately 2 to 3 times higher than those of nautiluses and even exceeded those of certain long-lived marine animals, such as modern-day parrots. This elevated metabolism had profound evolutionary consequences. A high metabolic rate is often correlated with accelerated developmental processes, shorter generational spans, and rapid reproductive cycles. For ammonites, this meant they could evolve swiftly, giving rise to a dazzling array of new forms through a process known as adaptive radiation. Their ability to exploit a variety of ecological niches allowed them to become one of the dominant marine groups during the Mesozoic era. In contrast, parrots, a modern benchmark used for comparison, take about 15 years to reach full reproductive maturity. Ammonites, on the other hand, are estimated to have reached adulthood in as little as 4 to 6 years, fueling rapid generational turnover and evolutionary momentum. This evolutionary engine was further supercharged during the Cretaceous period. Atmospheric oxygen levels rose significantly during this epoch, providing an ideal environment for high metabolism organisms like ammonites to flourish. The ocean teemed with life, and ammonites became both predators and prey in a highly dynamic ecosystem. Their suture patterns, intricate lines formed where the internal shell walls met the outer shell, became increasingly complex, reflecting their specialization and diversity. These patterns are so distinctive that modern paleontologists use them as precise tools to date rock strata and reconstruct ancient environments. However, the very trait that once gave ammonites their evolutionary edge eventually contributed to their downfall. 66 million years ago, the Earth experienced one of the most devastating mass extinction events in history, the Cretaceous Paleogene (KPG) extinction. Triggered by a massive asteroid impact near the Yucatan Peninsula, this event unleashed a cascade of ecological disasters. The impact generated massive wildfires, global darkness from airborne particulates, and crucially released vast amounts of sulfur oxides into the atmosphere. These compounds mixed with water vapor to produce highly acidic rain, which subsequently increased the acidity of the oceans over time. For ammonites, which inhabited the upper layers of the marine environment and relied heavily on plankton as a primary food source, this was a double blow. First, the acidified waters began to dissolve their delicate calcium carbonate shells, making them vulnerable and unable to maintain buoyancy or protection. Second, and more critically, ocean acidification and the collapse of photosynthesis due to prolonged darkness decimated plankton populations, the base of the food chain. With food sources disappearing and a high metabolism demanding constant energy intake, ammonites found themselves in an unsustainable situation. Their physiological needs became liabilities in a world where survival demanded frugality and resilience. In stark contrast stood the nautilus, a distant relative of the ammonite and a model of evolutionary conservatism. The nautilus has maintained a relatively unchanged body plan for over 490 million years and inhabits deeper ocean layers, typically between 300 to 700 meters below the surface. This depth not only shielded it from the immediate effects of surface-level acidification, but also insulated it from the most drastic fluctuations in food availability. Unlike ammonites, nautiluses have a much slower metabolism, enabling them to survive on minimal resources. They scavenge detritus and feed opportunistically, requiring far less energy input to sustain themselves. Furthermore, their reproductive strategy differs significantly. While ammonites are thought to have released thousands of tiny eggs into the plankton-rich waters, leaving their offspring at the mercy of environmental conditions, nautiluses lay fewer larger eggs that they anchor securely to rocks on the seafloor. This not only protects their young from predators and acidic waters, but also ensures development in more stable conditions. In essence, what doomed the ammonites and spared the nautiluses was not just a difference in shell shape or habitat, but a profound difference in biological tempo and ecological strategy. Ammonites thrived on rapid innovation, specialization, and metabolic intensity. Nautiluses survived through slowness, adaptability, and endurance. The story of these two cephalopods serves as a poignant reminder that in the grand narrative of evolution, it is not always the most diverse or dominant species that survive upheaval, but those most capable of enduring change. The practice of consuming carrion rather than plankton significantly enhanced their survival prospects. Ammonites reproduced by releasing little eggs measuring between 0.5 and 2.6 millimeters into the water, resulting in their eggs being exposed to acidic waters. Conversely, the clam reproduces by affixing its sizable eggs around 3 centimeters in diameter to rocks on the ocean floor. This was comparatively secure, allowing the nautilus to perpetuate its lineage. However, the matter at hand is as follows. A question emerges here. Despite the survival obstacles faced by ammonites, Their remarkable diversity during the Mesozoic epoch would ostensibly increase the likelihood of at least one species enduring and perpetuating its lineage through major extinctions. Nevertheless, there exists a little misconception in this context. A trait that arises during the process of speciation in an organism is ecological specialization. This denotes the phenomena wherein distinct species mitigate competition by optimally adapting to certain food sources and habitats, hence minimizing overlap in their resources and environments. Nonetheless, this specialization is highly susceptible to significant environmental alterations, such as mass extinctions. Consider a somewhat exaggerated scenario. Imagine individuals who are ideally optimized for drawing with a pencil on paper, those optimized for using a brush, others optimized for utilizing a thick marker, and individuals optimized for employing a fountain pen. Imagine a society where everyone is trained to master only one writing tool, pencil, pen, or brush. Now imagine that suddenly the world switches entirely to digital tablets operated by touch. Those who once excelled in their specialized tools now find themselves ill-equipped for this radical shift. This metaphor closely mirrors the evolutionary fate of the Ammonites. As Earth's environment underwent cataclysmic transformations at the end of the Cretaceous period, including massive volcanic activity, a plunging global temperature, and an asteroid impact, these highly specialized marine creatures faced an ecological crisis they were not prepared to overcome. Ammonites, once thriving with extraordinary diversity, ranging from small spiral forms to giants over a meter in diameter, had adapted with extreme ecological specialization. Their elevated metabolic rates, a key factor in their rapid growth, reproduction, and evolutionary radiation, also became a double-edged sword. While this high-energy lifestyle had fueled their success during stable periods, it rendered them incredibly vulnerable during times of environmental upheaval. When ocean acidity spiked, food chains collapsed, and surface ecosystems destabilized, Ammonites could no longer adapt quickly enough. Their specialization became their downfall, too finely tuned for a world that no longer existed. In contrast, the Nautilus, an ancient and seemingly modest cephalopod that predates the Ammonite by tens of millions of years, endured. While the Ammonite line was abruptly extinguished after 350 million years of evolutionary persistence, the Nautilus continues to survive in Earth's oceans to this day. However, its survival was not guaranteed nor without challenge. Approximately 28 million years ago, even the Nautilus began to feel the strain of shifting ecosystems and encroaching threats. Originally, scientists theorized that climate fluctuations during the Ice Age and shifts in oceanic circulation patterns were to blame for the Nautilus's dwindling range. But a 2022 study led by paleontologist Stephen Killback of the Swedish National Museum of Natural History offered a new perspective. Killback's research traced the rise of early pinnipeds, ancestors of modern seals and sea lions, to the same regions and periods during which Nautilus populations began to decline. These new marine predators, agile and efficient, may have found the slow-moving Nautilus to be an ideal food source. As pinnipeds spread from North America into Europe, South America, and Africa, the Nautilus's habitat shrank drastically, forcing it into isolated pockets of the Indo-Pacific. Today, Nautiluses are found primarily in the deep tropical waters of Southeast Asia and Oceania, often at depths of 300 to 700 meters, where colder temperatures and low-light conditions have helped them avoid extinction. Their ability to feed on carrion, survive on sparse resources, and lay large rock-attached eggs in safer environments has been key to their continued existence. This evolutionary tale offers a powerful lesson in nature. Survival does not always favor the swiftest, the strongest, or even the most intelligent, but rather those capable of enduring change. There are no permanent victors or losers in the evolutionary arms race. Species that dominate one era may vanish in the next, while humble survivors like the Nautilus quietly outlive their flamboyant contemporaries. Evolution, it seems, rewards not just adaptation, but resilience and sometimes simplicity. What do you think? Do you believe our modern species are heading toward the same fate as the Ammonites? Or can we learn to adapt like the Nautilus? Leave a comment below and share your views. Don't forget to subscribe to the channel so you don't miss out on the next exciting scientific discoveries.